All right, now for linear motion, we use the mass to describe the inertia of an object. And remember, if an object had a lot of mass, then it took a lot of force to get it to move, to give it acceleration. That was defined by Newton's second law, right? If it has a lot of mass, it's going to resist any changes in motion. Whether it's moving, it's going to be hard to stop. If it's not moving, it's going to be hard to put in motion. Now, for angular motion, we're going to have something very similar. It's called the moment of inertia. And it describes the inertia of the rotating body. So this moment of inertia, which is going to be related to the mass, but not just the mass, this moment of inertia will describe how easy is it or how difficult is it to put this object into rotational motion. So the moment of inertia describes how difficult it is to change the rotational motion of the object. The rotational motion of the object. We're going to define it in this way, and I'll show you where this comes from in just a bit. But we're going to define I as the sum of mr squared, where m is the mass and r is the distance from the axis of rotation. So m is the mass, r is the distance to the axis of rotation. Now the units of moment of inertia are kilogram meter squared. Mass is in kilograms. R is in meters, kilogram meter squared. So let's consider a very simple arrangement of particles. These particles, these are just discrete particles. I have a 3 kilogram mass that's 1 meter from the axis. They're rotating about this axis in this direction. I have a 1 kilogram mass that's 2 meters from the axis and a 2 kilogram mass that's 3 meters from the axis. If I want to know the moment of inertia of this system, it's going to be the sum of mr squared. That is going to be 3 kilograms times 1 meter squared plus 1 kilogram times 2 meters squared plus 2 kilograms times 3 meters squared. And that gives me the total moment of inertia of the system, which is 25 kilogram meters squared. I just take the sum of all the individual particles and I add them all up, mr squared for each individual particle. Now with calculus, we can calculate the moment of inertia for other objects. We won't use calculus, but it's fairly simple here for this one, so I'm going to show you. Let's say that I have a thin hoop, right? That thin hoop is rotating about this axis. Say it's rotating in this direction in the plane of the page. I can break it up into a whole bunch of little pieces. These are called differential elements. They're really small, okay? And I break it up into a whole bunch of these. Now, if I want to know what is the moment of inertia, I'll just say I is equal to the sum of mr squared. That's the definition for the moment of inertia. As I said, we'll get to this in just a bit, but like where that comes from. But it's going to be m1 plus m2 plus m3 plus however many other differential elements I break it into times the distance from the axis of rotation, which is right here in this case, so it's the radius of the hoop. Now, this is just an integral, so if you're in calculus 2, you'll recognize that an integral is really just a summation, and so it is the integral of r squared dm. And in this case, r doesn't change, so for a hoop, that is, for each of these little mass elements, they have the same distance, and so it's just going to be mr squared. And so that is the moments of inertia for a hoop. I have a table here that gives you moments of inertia for various physical objects. For a hoop, a cylinder, rod, what have you. We'll deal with that next.